Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel, we talk about all things Gen Chem related. On this video, I'm going to be covering solution stoichiometry and how we're going to couple our molarity-based calculations with the stoichiometry stuff that we covered in previous videos. Let's get started. So if you recall back to when I introduced the mole bridge idea, we discussed about the fact of how we have this bridge and our first point of action is to get to moles. And what we previously said was that we would use mole island as a means to get to and from moles. So that's using the molar mass as well as Avogadro's number. Well, now that we know how to actually quantify the amount of substance that's found in a solution through those molarity calculations, our molarity formula also becomes another way that we can get to moles first based on the information that's provided. And so you have to look at what's the information I'm given, what am I solving for, to determine if indeed you want to use some portion of mole island or this molarity-based formula to get to moles first. Similarly, on our other side of mole island, or other side of mole bridge, depending on what we're solving for, you could then also use mole island to continue on, or that molarity formula. Again, we're going to keep adding to this mole bridge as we move through this chapter and next. So keep this as a great reference point. Again, our first step is always to get to moles, and we do so either using mole island or the molarity formula. We then use that mole to mole ratio to cross the bridge, and then continue on using either mole island or the molarity formula to solve our problem. And so we're once again going to harness and use the fact that we have these inherent ratios that exist between the moles that are present. And so let's take a look at a problem like so. It says, what volume of 0.15 molar KCl is required to completely react with 0.15 liters of 0.175 molar lead to nitrate in the reaction that's shown here. And so again, let's go ahead and write down what we know. We're looking for the volume of the KCl, and we know that it is 0.150 molar. And some other information we know is that we have 0.150 liters of the other reactant and 0.175 molar lead to nitrate. And so in this case here, we want to take the information we know about one reactant to help us to predict information about the other reactant. So our bridge, the only place that we can start and find moles at this point is from the lead to nitrate. And so we're going to start with that and connect our bridge backwards, okay? Now, problems like this, students often see this and they get very excited because they say, oh, I'm solving for a volume, I have a molarity, I have another volume, I have another molarity. So therefore, I surely must be doing the dilution problem, M1V1 equals M2V2. However, that dilution formula is only used when you are dealing with taking something, one solution, and making it less concentrated by simply adding more solvent. You're not reacting with anything. If you see that you have a reaction taking place, you're not going to use that M1V1 equals M2V2 formula. You need to go through the stoichiometry steps to solve it. So in this case, because I have a molarity, because I have a volume of lead to nitrate, the only way I can get to moles is through that molarity formula. And so if I rearrange my molarity formula, which we know is moles over volume, and if I solve for moles of the lead to nitrate first, first step, what I would end up doing is plugging in to solve for my molarity, which is, solve for the moles, which is 0.175 molarity times the volume of 0.150 liters. And you can string this into one long stoichiometric step, by all means do. But if you like to piece it out, that's fine as well. So you can do 0.02625. Again, that would round to 0.0263 because of sig figs. okay? After you have your mole amount, we then get ready to convert from mole to moles. So 0.0263 moles. We're just going to round that up here of PbNO3, 2. And now we're going to use our mole to mole ratio, which is 1 mole of PbNO3 2 compared to 2 moles of KCl. When you plug in 0.0263 times 2 moles of KCl divided by 1, what you end up getting is 0.0525 moles for the KCl. To get the volume, we would then take that volume amount, set it equal to the moles divided by the molarity. And so we can then plug in our mole amount of 0.525 moles divided by the volume of 0.150, excuse me, the molarity of 0.150. And so what that then gives us is 0.350, 0.0, so what that will give us is 0.350 liters as our final. So what that gives us is 0.350 liters as our final answer. Problem, and this time I am going to try to string things together using just the simple unit conversion and dimensional analysis that we know. So this says 43.8 milliliters of 0.107 molar HCl is needed to neutralize 37.6 milliliters of barium hydroxide solution. What is the molarity of the base? And so again, here, the base in this case is barium hydroxide. So we're looking for the molarity. We know that the volume that we have is 37.6 milliliters. I'm just going to go ahead and write that as liters because we know we need to convert those volumes to liters. And we know that we also have 0.107 molarity and 0.0438 liters. And so if we multiply those two things together, we know that that'll allow us to get to moles first, and then we can continue on our pathway, okay? So first step is to get to moles as always. So our moles of HCl would be equal to the molarity times the volume. So 0.107 molarity times the volume of 0.0438 liters. Again, for those molarity calculations, you must be in liters. 0.107 times 0.0438, and that gets us 4.68, with some numbers repeating, times 10 to the negative third moles of HCl. We know that the next step is then to use the mole to mole ratio. We want to cross the bridge. So moles of HCl on the bottom, that'd be 2 of them, is to 1 mole of barium hydroxide. Okay, so we divide that answer by 2, and we now end up with 2.34 times 10 to the negative third moles of barium hydroxide. So then the last step to get our molarity would then be the mole amount divided by the volume. So we would take the moles, 2.34 times 10 to the negative 3 moles, and divide it by the volume of 0.0376 liters. And what we end up with is a molarity of 0.0623 capital M for our final answer. I hope this video helped you understand how to do solution stoichiometry problems. Make sure you guys like, comment, and subscribe, and let me know what kind of content you'd like to see. See you guys in the next video. Talk to you later. Bye.